And Dr. Lee, you can share the screen and can start. Thank you so much.
Yeah, can you please share the I
Yes,
cannot
I
share
think we
my
can do it.
screen.
We can
Okay.
do it.
Now yeah. Okay. Okay, can you see my screen?
Oh, can you try one more time?
Oh.
Yeah.
Okay.
Yes.
Is it okay?
Yes, working.
Okay, thanks for the introduction and inviting me to this webinar series. It's my great pleasure to talk about my research in the COXIA webinar series. So as the chair introduced me, I was a research scientist in Google for the last 10 years. And during the last 4 years, I started dual employment with the Seoul National University. And I spent really happy and nice and busy 4 years. And finally, I decided to quit from Google and focus on my research at university. So I came back to Korea in this March. And yeah, now I'm working as a full-time in Seoul National University now. So in today's talk, I will talk about my 3 recent work in focused in my group. So if you're interested in this work, I'm open to more deeper discussions or potential collaborations. Just feel free to ask me any questions or send me an email. So the very general introduction of AI research trend. So if you think of an AI as an agent, just like a human, we interact or communicate with AI in 2 directions. In the first part is from the AI perspective, it should be able to understand the world it lives. It should be able to read text just like humans or see the visuals and sceneries and understand the semantics of that and so on. So that is called perception. And you know, the vision transformers or CLIP or recently the VLM models are performing these really well. And the other direction is generation. So AI also should be able to generate some artifacts like texts or images or videos or audio, which can be consumed by human. So as you are already familiar with, the ChatGPT has started this service a few years ago, and Gemini from Google or Phi 3 from Microsoft are following the similar kind of services. And now we see that during the last 10 years, these perception and generation are developed to the human or even superhuman level. And now we are able to communicate with AI just
네,
as
혹시 유민경 선생님이실까요?
just as we do with other human. So once we have these technologies, actually we can do the interaction with the AI in for more complicated downstream tasks. Something like image manipulation or recommendations or any other very complicated tasks. And my group are working on all of these 3 aspects, especially on representation learning for the perception and generating images and videos, mostly for the generation part. And recommendation systems is the most prominent application that my lab is focusing on. So in today's talk, I will talk about 3 works, 2 from the representation learning, which is the referring image segmentation and video summarization. And from the generative modeling, I will talk about the initial work done in my lab for the image editing. So the first work is the referring image segmentation, which I presented in the last year's ECCV with Chaeyoon, which is my master student. So definition of the task. So referring image segmentation task is like this. We are given one image and a text describing some object in the scene. So for example, in this scene, our task is to segment the object indicated by the query text. For example, here, a young woman in blue shirt and striped pants sitting in the snow. Then our task is to find out this lady and segment pixel by pixels. That's the expected outcome. For the same image, if we get a different query, like a skier in an orange jacket bending over, then the answer changes to this lady. It's very intuitive and simple task for human, at least if the object is actually seen clearly. But for machines, it's a little bit complicated. So we found out that the level of difficulty of each instance is very different from by the given image and the query. So for example, in this image, we see that a lady is pointing something in the traffic signals, and we see a parked car. If the text query is given with the second one, a parked white Ford SUV, then it's a relatively easier question because we have only one car, one SUV in the scene. So we actually don't need to really understand the detailed description of this object. But given just that word SUV, then this is the only answer. Because in this particular task, we just assume that the pointed object exists in the scene. So it's really simple question. But if the query is the first one, a sign lettered Annie between woman and SUV, then we see three traffic signals here, the first one, second one, and third one. So now we need to really understand the detailed description of this sign, lettered Annie, and it's between the woman and SUV. So depending on the level of difficulty of the linguistic complexity and the complexity of the scene itself, the difficulty of each RIS example is very different. So we hypothesized that the current RIS models perform really well or not, depending on this level of difficulty in each sample. So usually, people just report the performance of their model on some predetermined test set of the existing data sets. So our performance is 64%, for example. But we did some breakdown on that eventually, the overall score. So we manually picked 100 easy and 100 hard samples based on this criteria. If we can find the same kind of object exists, more than one exists in the same scene, then the model needs to understand the detailed description of that object. So, for example, in this one, this example is an easy example. A little girl in a blue dress, and there's only one little girl here. So it's really simple question. But at the bottom, an uncooked pizza with 4 hot dogs, we see at least 2 or maybe 3 uncooked pizza here. So to determine which pizza is the right answer, we need to, for the human as well, we need to figure out which one has 4 hot dogs on it. So if we can find more than one pizza, then that belongs to the hard samples. And we measured the performance of each existing models on these manually crafted test sets. We see that on easy samples, the performance goes up to high 70s. On the other hand, on the harder test sets, the performance drops to like 40 or 50%. So this one indicates that these current models are really performing well only on the easy test sets, while they are not really working well on the hard samples. And even in the same data set, actually, there are a variety of difficulty levels for those examples. For example, the Ref Coco, which is known to easy and simple data sets, because this most of the queries are really short, like right woman or the woman, and that actually indicates that only one woman in the scene. But the harder data set called GREF, it has more complicated examples like this. There are at least 2 or 3 women in the scene, and a woman getting her hair brushed, then we need to understand who is actually doing that. So the key idea is, when we train the model, it would be nicer and more helpful to give harder examples to train the model in a fine-grained way. Then it will be able to perform well on the harder examples. But the current models were not able to doing that because the data set itself is limited, because they contain mostly these easy examples. Even in the harder data set, like GREF, many of the examples are still easy, like this. There's only one lady holding a glass. We don't need to actually understand all of these descriptions because just one lady is here. So how can you make a harder data set? One obvious, straightforward, expensive way would be collecting complex images and letting the annotators to write a text about that, which is very costly and time-consuming and expensive. So our idea is, instead of just using a single image as a training data set, we just randomly combine 4 different images in a 2x2 mosaic manner, and only using one of them as a ground truth. So for that ground truth, we take the annotated text, and then the answer, the segmentation answer for that particular object becomes the answer. So for example, on the right one, we cannot find a woman standing in front of the wall if we just find a woman. It still needs to understand who is standing in front of the wall, as opposed to the original example. Because there's only one woman here, it's really trivial question, and the model just ignores, it can actually ignore the description of her. But if we give this 2x2 mosaic to the model, then because we have multiple women here, the model still needs to figure out which woman is the referred one. So that's our very simple idea, just augment data to give more complexity to the model. But as you know, life is not that easy. So we have tried just randomly organizing 2x2 images, and a woman or man or a person might work, because in many photos we have a lot of people. But for most other objects like pizza or flower or car, most other things, we don't have that much objects in this image data sets. So if we just randomly assign 2x2 images like this, still in only one image we can find a pizza. So it's still easy. So what should we do? Nowadays we have good embedding models like CLIP. So using the CLIP embedding, we can compute the similarity between 2 images or between image and a text very easily and robustly. So can we mine some negative examples, which is very close to the positive one, so that the model is to be trained to distinguish those negative objects and the positive object based on the description. So what we tried is, given this text query, a man jumping with a skateboard, we tried to find the most closest images from the data set. And those 3 negative, most similar examples and 1 positive example are combined as a 2x2. And as you see here, all 4 of these are a man jumping with a skateboard, because they are too similar. And based on this description, even a human cannot find out which one is the intended one. They are perfectly correct ones. So giving a model as a training example with this image and this text and find out who is the referred one is invalid question, because all 4 of them are correct. At least more than 2 are correct, then it's not a valid question to the human, right? So this one gives an idea that it should be not too easy, but at the same time, it should be not too hard. So what would be the proper level of difficulty? So we built a pipeline, which is very intuitive. So we sort all the images in the order of the similarity to the query. And then we take out the top 12% of the images because they can be too similar, and that might make some invalid questions. So this is a hyperparameter, and this is the value of tau depends on the data set. And once these are took off, then we take the top k of the remaining images, and this k is another hyperparameter. So if k is 3, that's the most greedy algorithm, that we take only the most similar 3 images as negatives in the remaining sets. Or if you can take k larger than 3, for example 20, then it gives a little bit of randomness. So top 20, except for the most 2 similar images, then we take 3 out of these k randomly, and then we can make this kind of mosaic. This k is another hyperparameter that needs to be tuned for each data set. So that's it. Actually, this kind of data augmentation can be applied to any model on any data sets, and we conducted these experiments with and without our negative mind mosaic, which is called NEMO. And as you see, in all settings, the performance boosts. So that was quite nice results. And from the left to the right, the level of difficulty on average is getting harder and harder. And interestingly, we see that the average performance improvement is actually increasing to that direction as well. So on the hardest data set, our data augmentation technology actually helps mostly, and that is aligns with our assumption. And this is the qualitative results. So on the left, you see that the generated training data with our method. So let's see an example. A lady in a black dress cuts a wedding cake with her new husband, and these are the training images we have found. Our method actually made. So this lady is the correct answer. But for the other 3 images, we see at least one lady in each of those images. And this one looks like a wedding, and this one holds a cake, and this one is cutting a cake. And here's another lady in a black shirt, but she's not with a new husband, and she's not cutting a cake. And she has the cake, but she does not wear a black dress. So these are in a proper level of difficulty. So as a human, we can find out who is the right answer without any doubts, but still need to investigate who is the right one. A little bit more thinking is required. So same for the AI. So these are kind of the right level of difficulty we were expecting. And in the end, we have seen some good examples that our model were able to find a good answer, and the baseline couldn't. It's like this: a man in a white cap and brown shirt standing next to an elephant. The right answer is this one. And this man is actually not really prominent in this scene. And the baseline models without our method, our data augmentation, they tend to pick the object which is most prominent in the scene, because it focuses only on the term man. But our model were able to actually find the right person in this kind of similar results in other examples too. So I introduced this work in the first because this is really intuitive idea. Actually, everyone in this room can come up with. And this paper was able to get accepted at the top conference ECCV in computer vision, mainly because I think the flow of the idea was really smooth, and it's generally applicable to all models in all data sets in this particular problem, which was kind of impactful. So yeah, if we are students working on the computer vision and research, I think this kind of development of the idea and execution and verification would be a good model for you to actually follow. And the next work I would like to introduce is video summarization, which is one of the most important topic that I'm working on in my lab. We have published this paper in NeurIPS 23, and we have another paper currently under review at ICCV, which is likely to be accepted. So what is video summarization? So you might think of some text-based summarization of a video, but here I'm talking about generating a shortened video containing the entire contents in a short budget. So given a 90 minutes soccer game, you may want to summarize it to 5 minutes long video, and still you want to grasp the entire story of the game. Or sometimes we just want to see the highlights, which these are highly relevant, but a little bit different. Highlights is just the most engaging and interesting moments within the video. Instead of, it doesn't necessarily really need to have the entire story summarized. But as you can imagine, this video summarization task is really challenging task, especially for because of these 3 reasons. First of all, it's really subjective. So if I ask all of the attendees in this room to summarize a movie or a soccer game, each one of you will have different opinions. So no same results will come out. Maybe some of them are quite similar, but still everyone has different opinions. Which scene is the most important thing to be included in this short budget? So there's no only one correct answer. Depending on the video, the summarization can be even more diverse, or some other videos may have some more converging answer. But still, it's very subjective, and there can be multiple answers. And because of that, it's really costly to create a large-scale data set. So imagine if you are creating a data set of video summarization, you have to watch, each annotator has to watch the entire video, and then they need to select the most important scene, part or clip of the video. And because it's a subjective task, you need to have multiple raters. So existing data sets usually have like 15 to 20 raters per video, and each of them actually needs to watch the entire video and annotate each frame. Very time costly, and if you need to pay them, it's expensive. Because of that reason, the 2 most widely used dataset called TVSum and SumMe, they have only 50 and 25 videos. We understand that this is really hard, very costly dataset, costly process to make this dataset, but still, in the era of deep learning, these are ridiculously small number of examples to train a deep learning model. And because of that, because researchers have relied only on these kind of small data sets, extreme overfitting atmosphere is currently going on. So we have conducted some experiments on these data sets. So this table summarizes. So the reported is the scores that is reported in the original paper. And we actually, all of these models release their source code. So we just ran them without any change, just ran them to reproduce the results. And as you see, the scores are just slightly lower, or sometimes it's a little bit better, but still quite different. It's still very similar, but it's not exactly the same. It's okay. Now we have detected that many of these models, actually most of these models, do the model selection on the test set, not having any set-aside validation set. If you're studying machine learning, you should know that this is really wrong way of model selection, because it will overfit to that particular test set, but will not generalize to unseen videos. So it does not really achieve these scores. We detected that, and we have changed the training and test the validation scheme to have the set-aside validation set from these small number of videos, and then select a model based on the validation performance, and reported the test scores on the unseen test sets. Then you see that all of them are dropped to 40 or 41, And this one also dropped to below 60. And surprisingly, this is not very different from the random score here. So recent works in video summarization, they didn't really solve any, not any, but mostly it's just overfitted results. It's not solving any video summarization task. So we would like to solve this problem, but the bottleneck is on the data. So we cannot generate or collect labels from for a large-scale data set. So we came up with an idea that on YouTube, you probably have seen that some statistics of this kind of graph is shown in some videos. You probably have seen that. These are called most replayed statistics. So it does not mean that people have seen that part a lot. It actually means people has replayed that multiple times a lot. So that's the statistics. And people has watched this part many times. For example, in the soccer game, the most interesting scenes are when a team makes a goal or some penalty kicks or something like that. And this is a kind of good indicator of the engagement of users, which means they are a good candidate for the highlights. So we take these statistics as a label for highlight detection. And because highlight detection is quite relevant to video summarization, even though they are not really equivalent, we actually trained the video summarization model on these labels, and we found out that that's actually working. So we proposed a new data set called Mr. HiSum, most replayed highlight detection and summarization data set, which contains 31,000 videos as opposed to 25 or 50 videos. And because we didn't really have to have the annotators, this is average over at least 50,000 view counts, which we can think of as a raters. So they are really robust statistics. And we trained our summarization model on this data set. And it says that the performance is better than just training on the TV Summer Summit. Once we have pre-trained on this larger data set and then fine-tune on the existing smaller data sets. And this is the most important contribution of this work. Previously, these small data sets, they have just 25 and 50 videos. So the validation set size was at most like 10, which is the 20% of the 50 videos. Obviously, that's not enough number. So how big should be the validation set? It's an important question. And we have tried this different size of validation set on our own data set with 25, 50, 400, 1,000, and up to 2,000. You see that at least we need 1,000 to distinguish which one algorithm performs better than the other. So these existing data sets are too small to train the video summarization model robustly. And using these data sets, we are now working on modeling side. And one of my students came up with an idea to apply the diffusion models, which is currently widely used in the image generation, to generate this summary vector, which is the vector of importance scores of each frame. And we submitted this paper to ICCV, and we got quite nice initial review. So we're expecting to present this in the ICCV in Hawaii this October. And lastly, I would like to talk about one work we recently have done in generation part of the model of our work. So identity preserving image editing. So here's the description of the task. So we are given one image X and a text prompt T, which contains the desired editing direction. Then our task is to output some image satisfying these three conditions. First of all, the output should be a plausible image. For example, this is an example of output for this input image with a man with yellow hair. then this one should be an image that we can recognize as an image, not just a random random array of the pixel values. And it should reflect the editing direction. So this person should has the yellow hair. And the last one, it should retain the rest of the images without altered. So except for the color of the hair, you should see the same person, and the identity should remain in the same background and the same pose and the same dress and everything. We don't want to change them. And Google has published this paper in 2023 that they have achieved this. So given one image and text description, the edited image actually reflects the change, and it doesn't change all the other details of the scene. So it's kind of solved if you see these examples. However, we downloaded that model and actually tried to give some random examples other than they already have shown in the paper. We see that the last condition does not really hold in many cases. So given this image, and we gave a prompt text, a woman wearing glasses, we get this kind of image. So yes, condition 1 and 2 are satisfied. This is a valid image, and the lady actually has the glass on her eye. But the identity of the person has changed, and the background has changed, everything has changed. So this kind of model cannot be used to edit, for example, your own selfie, and you don't like your smile, you just want to make you a little bit more smiling, then you can give a prompt like, I would like more smiling face on my scene, but it will change you to a completely different person, which is useless. And this is a problem that is tackled in many different works, and we found out that this is even more challenging if we have multiple objects in the scene. So when we have a new single concept, for example, this is a toy, and if you'd like to name it and generate an image with some other objects like this, these are the expected outcome. And if you have multiple pets, for example, your own cat and dog, you may want to generate some images containing both of them at the same time with some texture queries as well. In reality, current AI models are not really capable of doing this. So for example, if you give this can image and the backpack image like this, and give a query that both of these in the beach, interestingly, it draws some images like this, very, very creative. We didn't actually train the model to do this, but they are kind of confused the concept of these two objects. So you see that the color of the two objects are exchanged to each other, or sometimes you see only the backpack but no can. But in the backpack, you see the logo of this thing, I don't know what it is, from the can. So they sometimes are blended. Attributes of different objects are actually merged into a single entity, or one of them is missing like this, or they are kind of mixed, attributes are exchanged to each other. So this kind of indicates that the embedding space does not distinguish the attributes of each object very clearly, and they are kind of entangled. So if you want to change one of those, it will change the other's attributes, and they can be mixed. Here's another example that a photo of toy and a dog at a beach. Then you see that the shape of these this toy has been changed to different shape or different colors or both. So existing works has tried to address this problem by giving a layout which explicitly indicates that a particular object should exist in which particular part of the image. Then they can reduce the chance of being blending those different attributes. But still, this is not a ideal situation because they require additional input, and it's really time consuming to generate this kind of training set and test set. So this is not solving the same problem. So our idea was to improve the latent space itself by distillation. So that's very simple but quite powerful idea. So in concept blending and concept mixing, they are happening because the latent space is not perfect, especially when we try to change when we try to fine tune the model with additional concepts like my toy or my dog. The existing latent space trained with very large data set is distorted, and it's the entangling actually happens during that process. So when we fine tune, we've claimed that this distillation with the existing model does help to preserve the original latent space as much as possible, and at the same time we can embed our new concepts more seamlessly. So these are kind of details. We give the distillation. This is the main the diffusion loss, which already exists, and we additionally give the distillation loss on the between our output and the teacher's output, which is the before the pre-trained is the frozen model. And we also give the distillation loss auxiliary between the intermediate layers between the student model and the teacher model, so that the student model does not arbitrarily change the embedding space of the teacher model, but they can keep as much as needed the original space of the embedding space, such that it's kind of balances to preservation of the original space and embedding a new concepts without hurting them as much. So this is the showcase of our current results. So we have submitted this paper to ICCV, but our review was not really good, so we are not expecting it will be accepted this time. But I still think that this is an ongoing work, and we are trying to improve the model and verify it in more. But here's an example. So these are the reference image. We would like to draw these in a new scene with some other objects. And you see that only ours actually preserve the original identity of these in detail. And also at the same time, it draws with a dog without missing any object. For example, this one, it's kind of combining the dog and this toy very creatively. Yeah, it's maybe another interesting direction to research. So yeah, thanks for your attendance today, and I did this quite quick because we are out of time and we want to have some Q&As and some discussion about my work and also my unique experience as a dual employment in a Korean university and a US company. So yeah, we can talk about that too. So these are the list of the papers that I just showed today. So if you're interested in, please feel free to read it. And if you have any questions or want to collaborate together, please let me know. So thank you.
Yeah. Thank you so much. So we receive like several questions. So I think there are like some question related to this talk. So let me introduce that question first. So how do you decide the number of samples to test when evaluating a generative models, and how do you design test hypothesis for non-deterministic behavior?
I'm actually looking at the question list as well.
Yeah, so that one is like a Jung Yoon's question.
Okay.
So how many sample size is good to test?
Okay. How do you decide the number of samples
Yeah.
to test when evaluating a generative model, and how do you design test hypotheses for large image? Okay. Yeah, it's a good question. It's as you can imagine, evaluating the generative models is really challenging because of the subjectivity and some other issues like model collapse. So to answer that question, we use 50,000 as a default, and that's widely used in literature. So it is kind of common sense that we at least need 30,000 to 50,000 images to compare the distribution between the ground truth and the generated ones robustly. So that's the number, and we just follow the settings that was used in the previous papers. And in some particular data sets or cases, we might need a little bit more, sometimes a little bit less, but you can adjust that based on the data set, and you can measure the standard deviation of the metrics, and if that's too unrobust, then you can actually try more. And also user studies kind of recommended. Many reviewers actually ask to conduct the user study, and we also do that too.
Yeah, there's another question related to like a video summarization. So have you noticed that popular scene tend to share obvious trait like loud cheers or laughter? So what difficulty do you encounter for that?
Most popular scenes tend to share obvious traits. Cheers and laughter. Well, interesting question. Unfortunately, the set of videos we are using for the training and evaluation is somewhat different from what you're thinking here. I think that kind of programs, TV programs like 무한도전 or other 예능 TV pros, they do have some laughters like that, and it can be a very prominent signals to indicate highlights. But TV Some and Some Me, they are the videos of documentaries, or actually just one of those data sets contain only scenes taken by just one shot. Something like airplanes are landing, and the kind of entire story is shown. So it does not have that much to answer that question. So yeah, I don't know. If we apply that to a variety of the data sets, maybe we will encounter that issue. Where I think the AI models will be able to find out that's highly related to the highlights, and it's a good thing. So yeah.
And so are there any promising architectures aiming to surpass a transformer in large language models? I think it's kind of interesting question in this area.
That's a really good question, and if I can do that, I'll be the next billionaire. So it's a very challenging problem. I think this is really important direction of research, especially in computer vision. So language model may be okay, but in computer vision, we have all the data in the pixel levels, which is much larger than the language, which is relatively abstract, meaning is stored in each word. But in computer vision, all the pixels has their RGB values, and even a small image, it's explosively large. So currently, we need to use lots of GPU resources to recognize very obvious patterns from those pixel level details. But we can think of this, that kind of representation, pixel level array or matrix, is only for showing the images or videos on the monitor, because the monitor is made in that way. Each pixel should be assigned with RGB intensity values, and then it shows its visuals seen to human. But if we store the images or videos not to show to human, but to feed into AI models, it doesn't necessarily follow that restriction. And human doesn't recognize visual images like that. If we see just a human, oh, okay, there's a person there, we don't really recognize the pixel level details. So there should be a better way of representing each image and video. And in the future, for example, like after 10 to 20 years, we will not be using this kind of large resources to compute pixel level details, obviously. So just like when we invented computer for the first time, now we have very huge machines and computing resources are required to process these kind of simple things. It will reduce anyway. And so figuring out the more efficient and better way of representing images and videos will be important research topic. And as a researcher in university, I'm interested in that kind of thing, like a more fundamental kind of stuff to improve the computer vision and machine learning.
So I think there are like a multiple very general questions. So what trait of human intelligence must be strengthened to stand against artificial intelligence in the AI era? So that will be like a first question in popular.
What trait of human intelligence must we strengthen to
Yeah.
stand? Okay, that's very philosophical question. I think the unique ability of human, which AI does not have, is the ability to ask questions. So AI will be able to answer most of human questions as long as it has data. And most data will be on the internet, so the AIs will be perfect to find those answers anyway. But it does not come up with any question. At least now, AI works or performs something only when it was prompted. But what would be the next question we need to ask to solve some problem? And what would be that problem is an important question. And if you would like to run a business, for example, what will be the thing that people will pay to buy what you're proposing? So asking questions would be the most important thing. And that's not easily replaced by AI, in my opinion.
And so the another question is, Dr. Lee has a very interesting career path and experience in both academia and industry. So can you share like the difference experience?
Yes, but before that, please, can you stop the recording for that part?
Oh, recording. Okay, just